Hi everyone, my name is Hendrik Bayer and my talk today is about a paper I wrote with Michael Kaisers on our first steps towards explainable Monte Carlo tree search. First off, motivation. Why do we care about explainable MCTS? We've actually proposed explainable MCTS, or explainable search in general, as a research challenge at the AAAI workshop just last month. So please do check out our vision paper there titled Explainable Search, or our video about it. Just as a small excerpt from this, the basic question we're interested in is, how can a search-based agent explain its behavior? This could be a chess AI or other board game AI as in the examples I will be giving today, but it could also be a self-driving car or a search and rescue robot, or a trading bot, or any other sort of AI that is using search, meaning online planning. Search algorithms like MCTS are at the heart of many recent breakthroughs in AI. In our vision paper, we've described a variety of interesting challenges around this, and today I'm presenting our first steps towards tackling some of them. We're working on a tool set for explainable MCTS here, a set of basic building blocks for MCTS explanations, which is why I'm going to very briefly lead you through 6 different techniques today. But first, a little bit of background for all of them. So how exactly can we derive explanations from a massive MCTS tree that contains information collected from thousands or even millions of simulated possible plans and possible futures? The basic idea underlying the following 6 techniques is this. When you explain a search decision to someone else, for example, a move in a game of Go, you typically say something like this. If you make move A, you strengthen the connection between these two groups. But if you make move B, you both help connect your groups and threaten an invasion into your opponent's territory somewhere around here. So that's the stronger move. What you're doing there boils down to 2 processes. In the first process, you simplify the enormous space of possible futures of the game to a few that you think are most relevant. You explicitly discuss only moves A and B. So in terms of MCTS, you pick a subset of the tree to use in your explanation. For example, the subset representing moves A and B, or their resulting states. This is what we mean by highlighting nodes in red on these slides, and we call it tree simplification. In the second process, you then decide what to say about that subset of the tree, about A and B. And you do that by comparing the expected consequences of these moves, which for MCTS means you compare the subtrees under move A and under move B. We do that by using a set of outcomes, or scenarios, that we assume to be intuitively understood by the explainee. In our example, connecting your own groups is assumed to be known as a good thing by any Go player, and having your territory invaded is assumed to be commonly understood as a bad thing. And now we simply look at the probabilities for those scenarios in all trajectories we've simulated following move A in the green subtree, and following move B in the blue subtree, and then we compare them. This is what we mean by highlighting subtrees in green or blue on these slides, and we call it subtree summarization. We cannot walk the explainee through every possible future, but we can abstract over possible futures by speaking of the probabilities of good and bad scenarios. The crucial point about scenarios for our explanations is that when we're using MCTS, we can treat all scenarios as random variables and compare their expected values under different plans. For example, what's the expectation of capturing your opponent's rook, given that your chess game trajectory starts with making move A, versus the same expectation when we start with move B. And this is exactly what happens when we're doing subtree summarization. And now I'm finally getting to the actual explanation techniques. There are 6 of them in total, in 2 groups. 3 techniques can be used to explain a search after it has already happened and is a done deal. Even though they can be interactive, they will not change the search outcome anymore. And 3 techniques enable the user to give feedback to the search algorithm, making some progress towards the idea of explanations as a two-way street, as a collaborative effort between AI and user that we're describing in more detail in our vision paper. We start with the first group that we call post hoc explanations. We've designed these as potential answers to 3 very basic requests for explanation. 1. Why this action? 2. Why not this other action? And 3. But what if this happens? The first technique is for answering the question, why do you recommend this action? The action that was preferred by the search, here marked in red. Our answer to this has 3 parts. The first part is presenting what in games is called the principal variation, or PV, which is just the most likely short-term future found by the search, explicitly shown over the next couple of time steps, for example until the tree's estimates become too uncertain to be sure. After doing a search from this state in a game of Connect 4, for example, on the right shown in the actual text-based format we're using because we haven't developed any graphical interface yet, we walk the explainee move by move through the near future that MCTS expects to be most likely, using text templates to make statements about how certain we are about each move. The second part of the explanation is a general overview of what MCTS expects to happen in the long-term future. This means simplifying the tree to only the current state, represented by the root node, and then summarizing all of it by giving the expectations for relevant scenarios. For example, in our Connect 4 position, we can use all possible groups of 4 disks as scenarios to summarize in which way the game is likely to be won by which player eventually. Yellow is currently 41% likely to win with the group shown in the top left, while it's looking rough for red, with no group having more than 1% probability. We can also show expectations for other scenarios in the form of heat maps. For example, here the probabilities for yellow or red making the eventual winning move on any given square of the board, which can help the explainee understand where to focus attention. Or we can show the probabilities of owning each square of the board at game end, where green and red stand for the 2 players. Which scenarios are most interesting depends on the domain. In chess, for example, we could also plot a heat map of the chances of each piece to survive the game uncaptured, or a heat map of where both players' pieces are likely to go eventually, all averaged over all simulations in the entire search. And now that the overall situation of the game, with short-term and long-term expectations, is clear, we can directly answer the user's request in the third part of the explanation, or the only part, if the overall explanation has been given before. A contrastive explanation why the recommended move is better than all alternatives. This means simplifying the tree to the recommended move and its alternatives, and then comparing summaries of the subtrees under them. In our Connect 4 example, we can show that the recommended move for yellow increases the probability of the winning group on the top left by 26%, compared to yellow taking any other move. And it decreases the chances of red connecting the 4 disks in the top right by 4%, meaning from 5% down to 1. We can also demonstrate that the recommended move makes it 14% less likely for yellow to win on d4, but 27% more likely to win on c3 eventually, and so on for any relevant scenario. For the question, why not this alternative action now, if the user thinks the blue action should be better than the red one, we can again show the most likely near future in detail, now comparing the principal variations through both contrasted actions. And we can again show the expectations for the distant future by summarizing two subtrees, now the ones under the two contrasted actions. And finally, for the question, but what if X happens? Asking what MCTS would do in a specific possible future. For example, in this state here, two actions in the future. We've implemented a simple set of commands with which to navigate the tree. So users can request why or why not explanations anywhere in the tree, not just at the root. Limited, of course, by the amount of data in the tree at that depth. Moving on to the collaborative explanations now, we're also proposing 3 variants. 3 ways in which the user can request additional search by giving their own thoughts as input back to MCTS. For the question, what if you think a bit more about this action? When the user feels that there's a promising action that MCTS simply hasn't explored enough. MCTS does some additional search in the direction it was asked to, which might or might not result in a change of its recommended action. And then if, for example, it did and found that the user was right, MCTS explains this change by showing the most likely near future in detail, comparing its old and new recommendation, and by showing its expectations for the distant future by summarizing the subtrees under these 2 actions in order to explain which one is better. For the question, what if you knew that the opponent will do this? Or what if you knew that this will happen in domains without opponents in general? We allow the user to specify constraints that they think will hold true in all possible futures and that MCTS might not have known about in its search. The entire search is then repeated, respecting the user-specified constraint, possibly leading to a different recommended plan. And if it does, again, the old plan and the new plan are compared in terms of the near future, step by step, and in terms of the distant future by summarizing consequences of the old plan and the new plan, now in 2 entirely different search trees. Last but not least, we also came up with a truly collaborative search mode, in which MCTS is given permission to proactively ask the user for input whenever that would seem helpful. When a future state is visited very often by MCTS, for example, it can pause the search and ask the user, "This state seems important for the plan. Do you have an intuition what to do here?" And if the user says, "Yes, I do," the user suggestion can be built into the search from here on out as a soft or hard constraint. If the user answers no, of course, MCTS can just continue normally. And finally, after MCTS and the user together have come up with a new plan, the new plan and the old plan are again compared in the same way we've seen before, in terms of the near future and in terms of the distant future, to explain to the user the influence of their own choices. And that's the end of my talk. Thank you very much for watching, and goodbye.